Swayam Prabha. Digital India. Educated India.
The percolation graph, keep adding the number of sites. You will hit a number of sites which are sufficient in number, that is the percolation threshold, beyond which the clusters form, electrical current flows, finite magnetism is there and so on. But this value is different for the same lattice depending on whether you define the problem in terms of bond percolation or site percolation. And why this is different, it can be seen from this graph. This is a removed site. Removing a site is equivalent to removing all the 4 bonds. But here, this is an intact site where one bond has been removed. So you can see that the percolation thresholds in the site problem and bond problem cannot be the same. And which one is larger? Site percolation has larger threshold than the bond percolation problem. Which means if I am removing bonds, I can actually remove many more of them. But if I am removing sites, because each site removes 4 bonds, I have to be careful. If I am just removing the bonds, I can remove some bonds which don't affect the site, it still remains connected. From that, this inequality follows. XS has to be greater than or equal to B, XB. I hope this is clear. And then let's see some numbers. If you consider various 2-dimensional lattices like square, triangular, hexagonal, honeycomb rather, then the square has, we have discussed this over and over again, a 0.59 site threshold. But what is the bond threshold? It's 0.5. 50% of the bonds should be connected, 50% should be not connected in the bond problem. 59 sites should be connected. 41 can be broken in the site problem. It's the same problem. And then one can do it for other lattices. Everywhere the site threshold is more than the bond threshold. But there doesn't appear to be any pattern. You tell me the lattice, I will tell you this is the threshold. And then what's the use of this kind of physics which goes into so much technical detail? We have to remember this site has this threshold, this side has another this kind of lattice has one threshold, another lattice, another threshold. That goes against the spirit of percolation theory, which is about universality. There is no universality here. Can we achieve some universality, like a single expression covers all kind of lattices and tells us the percolation threshold? Can you think of some idea? Can you see which ones have a higher threshold and which ones have a lower threshold? Hexagonal 0.7, square has 0.59, triangular has 0.5. What is different between these? Number of sites? Total number of sites. But total number of sites I can always play with. I can make a bigger square and a smaller square. So that can't be the total number of sites. Yeah, number of neighbors. Bonds may or may not form, but neighbors are definitely there. You can see here the square has 4 neighbors, nearest neighbors. A triangle has how many? 1, 2, 3, 4, 6. Whereas this one has only 3. If there are less neighbors, you have to be careful, don't remove many bonds. If there are more neighbors, you can actually go on removing more bonds, which looks very intuitive. So let's look at the number of neighbors, 6, 4 and 3 for triangular, square and hexagonal. If you multiply these two quantities, xb and the number of neighbors, that is zxb, z I am calling as a number of neighbors, then that's a value 2 for every lattice, 2.1 to 2, almost the same. So that this is universality. Given any lattice, we understand what should be the percolation threshold. It just depends on the number of neighbors. But this exercise could be repeated for 3-dimensional lattices. What is the number of neighbors for a simple cubic lattice? 3. How many still say 3? I don't agree. 6. The reason is that I have just shown you a section of the 3D lattice. If you make a complete lattice, then 1, 2, 3, 4 in the plane and 2 up and below. So Z is 6. And XB was 0.5 for the 2D square, the bond percolation threshold, half the bonds, but this is a 3D one. Can we say anything about it? Well, I haven't solved it, but you can think of this idea. There are multiple planes. You are removing bonds from each of these planes. This is the 3D cubic lattice. In a square, the conditions are more stringent. 50% bonds are removed, it stops. But in a 3D situation, you can actually remove more bonds, because when the current is blocked in one layer, it can go on to the next layer. So intuitively, you can see that it should be something which allows a lower percolation threshold. Things are not available in the plane, but I can go one up or one down, and there I can continue propagating. So it so happens XB is only 0.25 for the 3D cubic lattice, not 0.5 for the 2D. And the reason why it is lower, I have argued. We can otherwise run the program or create a structure, do the experiment, you can prove these things. Right. To a 2D lattice, yes.
Couldn't you apply the same logic to a 2D lattice with more neighbors? Like the triangular lattice has more neighbors. But then there we still see Z into XB is roughly 2.
Right.
So why is it that here it's 1.5 but there it's 2? Because it's not just
so here
number of neighbors.
So what we are doing is each of these problems is exactly solved for say one cubic lattice, square lattice, triangular lattice. We are trying to see if there is a pattern. And within the 2D lattices, we found that there is a pattern, you multiply them, you get 2. But for the 3D lattices, when you multiply, you get 1.5. And then you can work with other 3D lattices. Maybe I can skip this section and come to the final result, where all the 3D lattice converge to a number close to 1.5. All the 2D lattices converge to a number close to 2. And this is because the property of percolation has an intimate connection with dimensionality. Its ability to percolate depends on the dimensions of the space you are in. To appreciate that, there is no board available, but I will maybe do a thought drawing. Think you are in 1D. You put a lattice in 1D, atom, 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 atom. What is the percolation threshold? It has 2 neighbors, each atom has 2 neighbors, so Z is 2. And what is the percolation threshold? Everything has to be there. So there if you multiply Z into B, you get 2. So 1D and 2D match. But 3D probably it allows you to go across different surfaces. So this number is different. So the take home message, percolation has a close connection with dimensionality, but then it obeys this universal property. Tell me the dimension, doesn't matter what lattice is there, I will tell you the percolation threshold. Z into XB is a constant that depends only on the dimensions of space. This has been formulated in terms of the bond percolation and shown as an example. XB is bond percolation. The question arises, is there a similar result for site percolation? As you remember, for the 2D square lattice, site percolation was 0.59, bond percolation is 0.50. What I have shown is for the bond percolation. For site percolation, we can think of this related quantity. You may say how many neighbors it has, but you can also say what fraction of space is being filled up. And this is called as a filling fraction. There is a difference. If the total space is here, and don't think of the color difference. I am looking at the intact lattice. If you have honeycomb lattice, nothing has been removed, then it occupies a certain fraction of the space. This is a part of the space is not available, this kind of star shaped structure, the curved star shaped structure. Whereas in a square, the space not available is shown here. That's the filling fraction, and if the filling fraction is more, you can remove more. If the filling fraction is less, you can remove less. And one can again, I won't go in the details, use it to arrive at a relation for the site percolation problem. Filling fraction into site percolation threshold is a constant that depends only on the dimensions of the space. And that constant is different from the previous constant. I hope the message is clear. We have gone faster with this part. And this is just a summary indicating what are Z, XB, F and XS. I hope they are clear to all of you. Okay. This is a topic I would, in view of time, actually skip. This a small topic I wanted to discuss, but maybe I can give a very quick summary because there was a question on that. What if the interactions are longer? Not just between the next spins, but they also influence far away spins. So I'll go over this part a little quicker. That means we allow nearest neighbor and next nearest neighbor and so on. Long range interactions, this site can influence a site which is far away. In our previous discussion it could not, electrically it still cannot, current can't jump, but in magnetism it is possible. And then if you take this square lattice, percolation threshold was 59% for the infinite cluster if you consider only nearest neighbors, Z equal to 4. But what if I make it next nearest neighbor? So this is the site, these 4 are the nearest neighbors, the next 4 are the next nearest neighbors in green. Then Z is 8, but XS comes down to 41%. And some of these spins will change directions as I have indicated with the red. Most of them will become up with this large cluster, but still this will not, because this is not a next nearest neighbor. But then you allow next nearest neighbor, n, then the number of neighbors are 12 and it comes down to 29%. At least in this picture it's more than 29%. So the infinite cluster has formed. Every site is pointing up. And then there are relations which, okay, one can say, forget the lattice. When you are having so many neighbors, next neighbor, next to next, next to next to next, it doesn't matter whether you are even in a lattice. You can be in random sites. And then this is the part I will not cover, but there is a problem associated with putting your elements on random positions in 2D or 3D, and it's the limiting case of long range interaction in the ferromagnetic problem. So let's skip this one, and there is interesting physics related to the Mott transition, which if you take up physics you might come across this at the college level. Now let's be with this interesting situation. We are interested in the behavior of this infinite cluster when it is forming. One question we answered when it will form, but can we say something more? What will be the structure of that cluster and so on? And here is the difficulty. If you take n equal to 4 small clusters, finite clusters, there are 19 ways of constructing them. Just n equal to 4 on a square lattice. And I tried to put 16 of them, then I got lost. Maybe I fell asleep. 16 clusters are there. Which is the 17th, I kept on thinking, I couldn't figure out, but there are 19. Then if you go to n equal to 5, 63 ways, and then this problem is best suited for sleep. 11 in the night, start counting the clusters. 19 of this type, okay, I put all 4 in a row, take 3 in a row, 1 up, so on. Then go to n equal to 5, 63, n equal to 6, and these are still very small. Infinite cluster you might be dealing with n equal to 100, n equal to 1000. How many such types will be there? So it's like counting these. In literature they are actually called as lattice animals. They are points on a lattice, but they are animals because they appear in your dreams or nightmares, and maybe they make you fall asleep. And this is the picture closest to what I had to say. This is how you counter lattice animals. Clusters near the threshold are very difficult to imagine. This is my infinite cluster. It goes in 3 dimensions. It has this very complicated shape, and I keep dreaming about it before sleeping so that I can fall asleep. That does not mean we can say nothing about it. It brings us to this problem, which I was interested to spend more time on as the concluding problem. The shape of the size of the clusters we can say something about, and we can also say something about how this rumor or fake news spreads. This problem can be formulated in 2 ways. So I will use the language of bonded and non-bonded, but you can think of it as transmitting and non-transmitting. Like Kenichi got this information, does not like to transmit. It does not like to form bonds. Whereas Ninja Hattori likes to transmit, so it is bonded. And we can say what fraction are bonded, and you can then connect it with this fake news problem. So this forms what is called as a tree. Start from one site. There are 3 neighbors. Then each of the neighbor can be called as a site, and this is next generation, origin, generation 1, generation 2. And here we have drawn a tree where there are 4 neighbors, but 3 neighbors belong to the next generation, 1 to the previous generation. This is how information spreads, but this is how many other problems can also be described. F is a fraction of reacted bonds. We have to give some number. What percentage or what fraction are reacted? What percentage of people are connected so that they are transmitting fake news? F. How many bonds are there in the cluster? Now you made a cluster of all these bonds which are there or not there. And how many bonds are there in the cluster? Start with the origin. And how many neighbors in the next generation? Z minus 1 neighbors are there. With the probability F, they are connected. Each of them is connected with the probability F. So the number of bonds becomes F into Z minus 1. If all are connected, it's simply Z minus 1. F is equal to 1. If none of them are connected, F is 0. Z minus 1 is the number of neighbors in the next generation. See here. Z is 4. So 3. Z minus 1, 3 neighbors in the next generation. Is it clear? Then for the next one, the previously connected ones have to make connections. So it's F into Z minus 1 again into F into Z minus 1. Because if it's not even connected in the first step, it can't form a cluster. So then you set up this geometric series, and then I don't have to tell you this. I'm sure you have learned this in school, how to sum a geometric series. But if not, you can see on the board. Then treating this quantity F into Z minus 1, that is forming the geometric series as X, then you know this geometric series will either go to infinite or will go to 0, depending on if it is more than 1 or less than 1. That means equal to 1 forms the threshold. It decides whether the number of bonds in the cluster, as the cluster grows to infinite size, the number of bonds becomes infinite or it goes to 0. 0 in comparison to the total number. Xc is 1, so Fc into Z minus 1 is equal to 1, because X was F into Z minus 1, which tells us what is the percolation threshold, Fc, for this tree. This particular problem is having a percolation threshold given by 1 upon Z minus 1. Z is the number of neighbors in total. That's a good result. And if, for example, you are working with Z equal to 3, that means you have 3 neighbors in all. You have 3 best friends with whom you share whatever rumor or truth or whatever you want to share. 3 best friends. Then on the average, I mean, this all maths is done with some kind of an average. Then each person talks to 2 further people. Somebody has told you the information and you are talking to 2 more people. The percolation threshold is 1 upon 3 minus 1, which is half. Then the result is that if you have 3 friends on average, then at least 50% of all the people should be involved in spreading the rumor, so that it forms an infinite cluster, An infinite cluster doesn't mean everybody knows it, but then it just spreads, explodes. That's where the explosion happens. And I feel very sorry because we live in the misinformation age. What do you mean Z equal to 3? Open the WhatsApp group, you have Z equal to 100. Z equal to 100 will give you a percolation threshold of 0.01, which means only 1% people should be forwarding your false information on WhatsApp, so that everybody from town to city to state to country and the world, there is an unhindered spread of that. Because Z is so large. This happens only in this age. The Z equal to 3 problems were the classic problems of 1960s. People were interested in that. Now people are looking at Z equal to 100, 1000 and so on. This also tells you why some things suddenly become a hit. I mean, forget rumors. There is some video on YouTube and that has got millions of hits. How that got achieved? So sometimes it could be Z playing the role, sometimes it could be the F playing the role, like what is a fraction, who are actually got interested with it and transmitting, but each person is transmitting to how many? This combination will decide the same. And if F is less than Fc, there is no infinite cluster, but if F is more than Fc, there is an infinite cluster which exists. And we would like to know one more question, the answer to one more question. What fraction of bonds belong to the infinite cluster? If an infinite cluster has formed, doesn't mean everybody who is transmitting information belongs to that cluster. You can think of it in the following way. Some people don't gossip, some people gossip. The ones belonging to the infinite cluster are doing the same gossip. There could be others doing gossip on other topics, right? So everybody need not belong to that infinite cluster, everybody who is doing gossip. The ones on the infinite cluster are the fraction of the bonded sites which belong to the infinite cluster. That's an interesting quantity. It's called the strength of the infinite cluster. To do that, you begin with the site, and for instance, it has 3 branches connected to it, 3 neighbors. Those neighbors again are further branched and there are sub branches. So there is this hierarchical structure, and we can impose this quantity Q just as an intermediary quantity, which is the probability that a site is not connected to infinity by one specified branch. It's a very long thing, not connected to infinity by one specified branch. Does it help us? Let's see. It's not connected to infinity means it's not connected to its neighbor, because we are looking at one specified branch. It has one neighbor, so it cannot be connected to infinity if it's not connected to the neighbor. And the probability of not being connected to the neighbor is 1 minus f, because f is universally the probability of being connected to a neighbor. So it's 1 minus f, that's one way. But the other way could be you are connected to the neighbor, but the neighbor is not connected to infinity. Then f is the probability you are connected to the neighbor, and the neighbor should not be connected to infinity, but not through you, through the remaining sites. So that is q raised to power z minus 1. Then this results in a recursive relation which can be solved, because q is on the left side, q is on the right side. That means we can find this quantity q. And let's take z equal to 3 because it's easy to solve in the class, and that gives us a quadratic equation which has the following roots. Q is 1 and q is 1 minus f by f. So we have found some quantity q, but that's not the quantity of interest. It's just for the moment we have found it because we are interested to find p. And then a similar recursive relation can be set up for p, and it's actually quite long, but I want to give you a feel of it, not that we need to really discuss this exact problem. If you are able to get it, good, otherwise we will move on. I will state this quickly. Probability that a site is connected to a neighbor, that is f, but not connected to infinity through any of the z branches. That means it has reacted but going in any of the directions, it's not connected to infinity, is f into q raised to power z. So what are these things which are connected to neighbors but don't connect to infinity? These are those bonds which are reacted but don't belong to the infinite cluster. So f into q raised to power z is f minus p. F minus p is total reacted bonds minus p, the ones which belong to the infinite cluster. And that allows for z equal to 3 to obtain a very simple expression which can actually be plotted out. And I'll make this plot. It looks like this. We have actually solved a complete problem. I was depicting to you various curves, and I was always focusing on the threshold up till now. But here I've taken a toy problem and derived the entire curve. If you plot whatever expression we got, the fraction which is connected to the infinite cluster is 0 up till the percolation threshold, because the infinite cluster itself doesn't exist. Then how can there be a fraction connected to the infinite cluster? Nothing. But then the infinite cluster forms, and more and more of them now start belonging to the infinite cluster as the f increases. When f is very, very large, that is, more and more bonds are reacted, more and more of them belong to the infinite cluster. And at the end it tends to 1, that is the highest possible. And then you can think of it, people spreading rumors 0 to 1, more and more of them are spreading rumors. Fraction belonging to the infinite cluster which are discussing that one particular rumor, that is 0, then that explosion happens. And after that it goes on increasing, and more people are discussing that one thing, which is this thing. And we can do an expansion of the result near the threshold, and it forms a power law, which is a property shared by many other phase transitions of second order, like ferromagnetic or superconducting phase transitions. So there is a lot of deep physics as to why this power law behavior is there. This is the number of sites belonging to that infinite cluster upon the total number of reacted sites, f minus fc, the difference from the percolation threshold, raised to power some power beta. Here in this problem we have actually shown beta is equal to 1. Okay. So this limited times, I will still try and describe more things about this infinite cluster. I might be going a little faster, but it's more about the feel of the topic, not all the details. You can always learn if you want to. When people looked at the infinite cluster, they found the following. You have reached the percolation threshold, and there is some lattice underlying it, and this infinite cluster is actually a very thin kind of a fish net which has just formed. Imagine there is a very narrow spacing of square lattice which are depicted here but you can't see, and then you just reach percolation, so that the current will flow along these paths, right? Along the green lines the current will flow, and in between two of them there will be thousands of square lattice points which are not depicted. And we can distinguish what is called as a backbone, because the current will flow through the backbone. Now, if I have an infrared sensor, that is where I will capture the heat. I will get a heat map which looks like this, because locally the current will heat those regions. And then there are dead ends which are also connected to the infinite cluster, but they cannot carry current. They are just like a wire which carries current. You put another wire touching it, though it belongs to the infinite cluster, but it can't carry current. So that is called as a dead end. Let's remove the dead ends. They are not interesting. At least in the current problem they are not interesting. Maybe in the magnetic problem they may be interesting. Then you can look at this backbone, which has a characteristic size called size of this fish net. It's a 2D square lattice. You've thrown a fish net, and it has some characteristic size. That is called in literature as the correlation radius, and it has a power law dependence. L, small l, is the lattice size, In the denominator you have bonded fraction minus the percolation threshold raised to power nu. Nu is called the exponent of the correlation radius. I will explain this a bit in the next slide. One can impose an imaginary square of L by L size on this fishnet and then ask the question, an infinite system has a well defined percolation threshold. That's what I gave as a take home message in the beginning. System is very large, it has a percolation threshold. But now if you are putting this square and asking, is there percolation in this finite square also? That question has the answer, it may or may not. Every small square may not have percolation, but as a whole it does have. Can we say something more? So we can say the percolation threshold of this L cross L square will actually lie in the vicinity of the percolation threshold of the infinite square. And how much in the vicinity? If you make L bigger and bigger, it lies closer and closer to XC. Nothing big has been said. Now let's plot this correlation radius R versus X. What is it physically representing? If you are less than XC, if X is less than XC, that is below the percolation threshold, then this is a quantity which diverges as you approach XC. The denominator is becoming larger and larger, smaller and smaller. X is closer to XC, denominator is smaller and smaller, R is going to infinite. And you can think of this as the growing size of the finite clusters. Small clusters, isolated atoms, bigger clusters, bigger, and when you are reaching the threshold, the size of the finite cluster itself becomes infinite. Seems reasonable. And then what about the right hand side? The right hand side is the mesh size in the infinite cluster. That is, the capital R is the fishnet you are throwing. When just percolation happened, that fishnet should be very sparse. It's an infinite fishnet. Before that, infinite does not exist, only finite which are growing. Once you threw that fishnet at percolation, it's a very rarefied fishnet. So R is infinite, and then it starts getting more and more connections. So then this keeps coming down. So this is why R plays an important role on both sides. But the meanings are slightly different. The functional form is the same. Now I can bring in L here because R is like a length, a correlation radius. So I can bring in length here. And if L is more and more, that is, if I keep increasing the L here, I can bring the L over here, that the size of that imaginary square keep increasing, then the spread keeps on decreasing. It is the delta keeps on diminishing. You can see it from this diagram. If L was put here, then this entire thing would have been your delta. That's the spread. If L is higher, spread is narrower. So one can actually say if the spread is X minus XC is delta, then R should be equal to L from that kind of a geometric argument. And that gives a power law dependence for delta. Delta is 1 upon L raised to power 1 by nu. There was a question why I wrote 1 by nu. So we are coming to that answer. Who had asked that question? Yeah, a couple of them. Yeah. And we can also connect the L of that imaginary square, L cross L square, with the number of sides. If you are in D dimensions, the number of sides is L, length of the square, divided by A, lattice period, raised to power D. D is the dimensionality of the space, because the square could be a cube and so on. And which brings us to this law about the spread of the percolation thresholds goes as C raised to power, C upon N raised to power 1 upon nu D, which was a law I wrote in the beginning of this talk, that you have this power law suppression of the spread of the percolation thresholds of the finite system, and we are able to describe it by virtue of this radius of the correlation radius. This is called as a size of critical region, and you can throw a net in 2 dimensions, you can also throw a net in 3 dimensions. People have done computer simulations and obtained values which depend only on the dimensionality. That is, nu is 1.3 if you are in 2 dimensions, it is 0.8 to 0.9 if you are in 3 dimensions. Yes, there is a question. C is just a constant you need not worry about. We are only interested in the dependencies. Finally, we may have to normalize it and say this is the actual value. So don't worry about C. So the route taken now, because you can't study infinite systems, is you study finite system of L cross L size and they have n elements, and then you can find what is xc, but it will keep changing for the finite system. And you can also find delta n, how much it changes from the average value. I did it 10 times on a computer with a finite system. I got this average value. This is the way it keeps changing. Then from that I can find nu, because delta n has a certain dependence on n. And then I can find the structure of this infinite cluster, because that's the fishnet of the infinite cluster. R corresponds to a property of the infinite cluster. There is no experiment possible and there is no simulation possible on an infinite cluster. But this is the linker. Something can be said about the infinite cluster, that what's the size of the fishnet and how it diverges to infinity by working on many finite clusters. I wanted to show this connection. This is the take home message. Maybe the math may or may not have followed, but please remember this. We have only 5 minutes to go. I will conclude in that time. This problem can be extended to the idea of electrical conductivity, so that from an abstract problem you can actually get a feel of something which is closer to real experiential world. Let's take this to be a unit square, and we want to know what's the resistance of this square just at the percolation threshold, where an infinite cluster has formed, that is, this fishnet has been thrown. These are wires which conduct and they have a size R on average. So the number of wires which intersect a unit length are 1 by R, because R is the size of that smaller square, L is the length here. Now I have taken it to be unit. It would be L by R, but now it is 1 by R because L is 1. And each of these wires is a parallel wire carrying current. So I can compute the total resistance. The total resistance for parallel wires will be given by 1 by R in the denominator. And that gives an expression for the conductivity. You can omit the steps, which has a power law dependence. The conductivity goes as x minus xc raised to power a power law. The exponent nu depends only on dimensionality. You may be working with many different lattice systems and measuring the conductivity of the system as a function of how much loading of the conducting material or the magnetism and so on. You will get this power law, which is in 2 dimensions an exponent 1.3. Similarly, you can do it for a net which is 3-dimensional, which will look like this. Now you will have parallel resistors, not 1 by R, but you have to look at the entire square and see so many of them are in parallel. That will give you 2 nu 3, which will be about 1.8.
Sir, so am I right in believing everything comes in terms of powers because of how one propagates to many more?
Why does everything come in terms of powers? That's the question. The idea where it comes from the power has to do with the concept of correlation radius, which is a diverging quantity which goes to infinite in a power law manner. And because you can connect that with the structure of that infinite cluster, which is actually diverging, then the conductivity or magnetic property also have the power law. And then this is a universal quantity. If this expression could be a take home message, the conductivity depends on this. I'll skip this. I just wanted to show some research work from our group. Some scholars are at the back seat. Vikas is here, who has studied percolation of protons and looked at the conductivity changes by 5-6 orders of magnitude. When you add some humidity to this system, which is like providing protons, because water can auto dissociate but can also interact with this material which can release some protons from the functional groups, and that will cause more conduction of ionic type. Like normally you have heard of electrons conducting, but protons can also conduct. The number of protons is being changed, which is like changing your X or F, and once a percolation threshold is reached, it can change enormously, and he has studied this power law dependence and so on, which is good for making a very sensitive humidity sensor. You add a slight amount of water, the resistance will change 10 times, then you can exactly know what's the humidity in the environment. And another stronger system is made with the hexagonal boron nitride by Anjan Das, who is also here. Here if you just add less than 5% of water, the resistance can be changed many orders in magnitude, and they all obey this power law, because you can plot it on a log scale, log scale here shown. Then log of the conductivity will go as linear, because if sigma goes as x raised to power nu, then log sigma will go as nu into. So here you can see that these are all linear and they obey this power law dependence that we just looked at. Interestingly, here the critical exponents are non-universal. It's none of those numbers which I depicted to you. 2D has this number, 3D has this number. It's only connected to dimensionality. But there are very rare systems. I can't go into the reason in this talk. There are very rare systems where unusual infinite cluster formation happens, and you can get exponents which are not described by the usual theory. This was one such system, and that is Anjan Das, who also plays football. Recently he won a medal for inter-IIT sports. The thing to conclude with this is nice picture of jelly. Is also one system where you have percolation, and this consists of when your mother may have made this, or maybe you yourself know how to make it, I don't know. It's in liquid form. You take some powder and pour some water into it, mix it, it forms a liquid. In that liquid form there are small polymers and cross linkers. It can flow, and then when it is allowed to settle, it starts forming this very nice structure which has good mechanical properties. You can touch it and it will kind of vibrate a little, and then this forms what is a gel. It's a soft solid, and gelation happens when the percolation threshold for the bond formation has been reached, and one can study the mechanical properties. Infinite cluster has been formed in this jelly. You apply some force to it. Only when the infinite cluster has been formed, it will behave like a jelly. And if you are too anxious, you want to have it very early, and you disturbed it early on, it will start to flow because the infinite cluster. So I wanted to show this example because you can relate. Next time you go home and say, I want that infinite cluster, make a jelly out of it. Okay, so that's all, folks. That's the end of the talk. I hope I could convey some important ideas in the theory of percolation. If any questions, please let me know. Okay, so the take home message would be cutting across electrical, mechanical is the last one, magnetic properties. You can have a universal description of various phenomena, and power law dependence is one important thing. Dependence on dimensionality is another important thing, and there is this quantity called percolation threshold which distinguishes. There are some connections with phase transitions that I could not discuss here, and this is it. So it was nice to get all interesting questions from you. All the best for the remainder of this program.
Sir, I just want to very quickly take this opportunity to extend a note of gratitude to you to take time off your schedule to come here and give us this very intriguing lecture. And I can surely guarantee you that your explanation not only it highlighted the magnificence of physics in simple sort of experiments and phenomena, but also it has ignited this sort of sense of curiosity in us to go and learn more and delve more into this topic. So once again, thank you very much, sir, for the captivating talk. And as usual, I also want to thank the RSIC committee and the teacher coordinators for the opportunity to attend lectures like these, so that we get our interest piqued and we can have some curiosity to learn more in the field of sciences. Thank you.